So I'm just going to wrap up this section a little bit with some thoughts on trying to do simulations and seeing how we can turn sort of general patterns like the island progression rule into testable hypotheses. In general, as ecologists and evolutionary biologists, one of the things that people spend a lot of time doing is just going out and doing observational science and characterizing patterns that they find in nature. So, in many of the examples that we've shown of the island progression rule, including the silver swords and many of the examples of island progression rule type patterns that they talk about in this paper in your Google Drive, um, the authors are really just they're showing a pattern, right? And one cool thing about showing a pattern, if you think you understand the processes that underpin the pattern, then you can go out into the world and find similar cases where, in this case, you want to look for other hotspot archipelagos like Hawaii. So, for example, the Society Islands, the Austral Islands, the Marquesas are all also different hotspot archipelagos. And so you want to be able to take lessons from what you know about evolutionary patterns in the Hawaiian Islands and potentially apply them to other island groups. And similarly, if you just look at patterns within the adaptive radiations that have taken place in the Hawaiian archipelago, like the silver swords, you might want to ask to what extent are the biogeographic patterns exhibited by silver swords also exhibited by other taxa within the Hawaiian archipelago. So observational science is sometimes given a little bit of a short, it's sometimes given short shrift when you're talking about it in terms of the broader context of the philosophy of science, because sometimes if you're just doing an observational study, there might not be as rigorous a hypothesis to test, and it's harder to do things like experimental design, for example. But observational science can help, illuminate the path towards helping you discover really grand patterns in nature, like the Big Bang Theory, for example, was arrived at after an astronomer whose last name is Hubble looked at patterns of stars and whether or not they were red shifted or blue shifted, and tried to relate that to how far away they were from us. So observational studies can yield really cool results. And sometimes they're also your only option. So it's hard to do hypothesis testing, good experimental design, manipulative field experiments if your question is, how do biogeographic patterns emerge in archipelagos, right? You can't just go out and create a huge archipelago and then wait millions of years for evolution to happen. So that's where simulations potentially come in. So I'm going to talk a little bit about some research that I did trying to demonstrate whether or not the island progression rule emerges in cases where I'm really simplifying the system a lot. And so this emerges from the desire to be able to sort of do predictive ecology and predictive evolution. So, for example, a few people have started to synthesize work that talks about generalizable patterns of diversity in islands, like the fact that it seems that if you just kind of squint at it, the geographic extent of the smallest island with speciation, so how big does an island have to be for speciation to be happening on that island for the different types of groups. So for bats, the island has to be pretty big for speciation to be happening. For mammals, the island has to be pretty big. For ferns, the island could potentially be a little bit smaller. Reptiles and birds, the island can be a little bit smaller. So this is in sort of the 10 square kilometer to 50 square kilometer range. And then for land snails, islands can actually be pretty small and still have speciation. So what's the size of the islands that you see speciation at versus what's the FST values at this sort of like 10 to 100 kilometer scale? So FST, if you recall, is a measure of population sort of dissimilarity, let's say, so population genetic dissimilarity. So an FST of 0 implies panmixia, right? So FST that's closer to 0 implies that, populations that are 10 kilometers apart or 100 kilometers apart are pretty much continuously interbreeding. There's not a lot of separation going on. There's not really separate subpopulations at the 10 to 100 kilometer scale. As FST approaches 1, that approaches the point where you would start to imagine that there's actually cryptic species there, that you're actually sampling multiple species. So FST at values that approach 1 imply that geographic scale at, the level of 10 to 100 kilometers is a substantial, it's an substantial impediment to interbreeding among the different populations. These organisms are kind of just lined up based on the FST and the sort of speciation versus island extent relationship. This is cool. And then you could kind of paint your own little pictures about how good these organisms actually are at dispersing based on their species traits. So obviously bats can fly, butterflies can fly, birds can fly too, but maybe behaviorally they're less inclined to cross certain types of barriers. And land snails, famously not that great at getting around. If you look within certain groups, so in this case, lizards in Australia, you might also be able to show that species traits correlate with, this is something kind of similar to FST. So in this case, how reduced the limbs on these lizards are seems to correlate with a measure of population divergence. But there's a lot of scatter, obviously. There's a line through this, but it's almost, the R-squareds are pretty low on this. So in some ways, we want to be able to move ecology and evolutionary biology towards kind of a more predictive science and start to ask questions that are set up as hypothesis tests, right? And so, hypothesis tests can often be in the form of an ANOVA design or, is this linear regression going to be significant, that kind of thing. But there are parts of ecology and evolutionary biology that are also really hard to predict. So famously, chaos theory was pretty much independently discovered by Robert May, who's a theoretical ecologist. And it doesn't take much complexity in a system to generate very, very hard to predict dynamics. And in kind of a more verbal bent, the question of how predictable ecology and evolution, and especially macroevolutionary patterns, how predictable should we expect evolution to be? How predictable should we expect ecology to be? Has been asked by Stephen Jay Gould, and then more recently by Jonathan Lossis. This book came out in 2017, and some of you read it, the Improbable Destinies book. I think one or two of you actually read Wonderful Life too, which was another potential book that you could have selected for the book review conversation. But both of these books have as their central question, how predictable is evolution? And Stephen Jay Gould came up with this often repeated, but now somewhat anachronistic metaphor of rewinding the tape of life. So if you could imagine letting the history of life play out and then somehow magically returning the YouTube cursor or whatever to the beginning of the video and seeing if it plays out the same way again. How repeatable should the patterns that you observe be? So you can ask questions like, is it inevitable that trilobites would go extinct at the end Permian mass extinction? Or is it inevitable that ammonoids would go extinct at the end of the Mesozoic? Is it inevitable that every non-avian dinosaur would go extinct? That kind of thing. Is it inevitable that humans would have evolved? So this question, this kind of body of questions, is asked, in a variety of different contexts by these two authors. And Jonathan Lossis has also written a lot about kind of adaptive radiations. And I wanted to try to ask this question about replaying the tape of life within the context of biogeographic patterns. And early on, it became really obvious that, of course, organisms with different types of traits should potentially follow different rules. You should see different patterns of biogeographic relatedness in the organisms of Hawaii, depending on what their species traits are. So if organisms are super duper good at dispersing, you might not see any speciation at all, right? So there are some taxa, there are some birds that live in Hawaii but are also found in other islands and they haven't speciated. Some of the ferns that are in Hawaii also have ranges that extend beyond Hawaii. Whereas land snails might exhibit very different patterns of biogeography. And so at this point, hopefully you figured out the sort of island progression pattern, island progression rule, style of pattern that we've talked about in a couple of other contexts in these videos, where island age, going from Kauai, the oldest, Oahu, second oldest, Maui, third oldest, and Hawaii, the newest island or the youngest island, you should see a phylogenetic pattern among the organisms that live in different parts of the archipelago that reflects the ages of the islands. So Oahu, Maui, and Hawaii were not available for colonization in the early evolutionary history of some clades in Kauai. So you might observe some combination of these sort of progressively nested paraphyletic grades. So maybe the taxa in Kauai aren't necessarily more closely related to each other than they are to some of the taxa in Oahu, but all the taxa in Oahu are more closely related to taxa in Maui and Hawaii than they are to taxa in Kauai, because there's been less time for diversification to happen in this part of the archipelago. And Hawaii might usually be expected to have kind of the youngest monophyletic clade. And the Shaw and Gillespie paper goes into a little bit more depth on this, where, you might expect, just based on island ages, Kauai is the oldest, Hawaii is the youngest. The taxa in Kauai should be more distantly related to each other than, or should be more distantly related to the taxa in Hawaii than, for example, like the most recent common ancestor of the Oahu taxa and the Hawaii taxa. And the most recent common ancestor of the Maui taxa and the Hawaii taxa should be more recent than the most recent common ancestor of the Oahu taxa and the Hawaii taxa. So you can have some combination of, these paraphyletic grades, monophyletic clades, but in general, the branching pattern and the pattern of the most recent common ancestors should reflect the age of the different islands in the archipelago, one would think. However, you can see that even, in this case, they're even showing the possibility that every once in a while there might be some back migration. So in this case, what this green dot is trying to denote is that this taxa is presently found in Kauai, but it is related to something that's from Maui. So this biogeographic pattern seems more unlikely, right? Because it would be hard for organisms to disperse backwards from Kauai to Maui, but like skip Oahu, for example. But in practice, sometimes you do observe small exceptions to this. So we saw in the Landis paper in this silver sword phylogeny that there are some examples of taxa, for example, within this Kauai clade. There's this one taxon that is found in Maui, I believe. Yeah, Maui. Yeah. So there are some exceptions to sort of the straight island progression rule, even though kind of if you squint your eyes, it still kind of looks more or less like the island progression rule. So what I wanted to do was actually use the island progression rule as kind of a jumping off point for testing this evolutionary simulation that I had been building to test a completely different set of ideas. But just the island progression rule made so much sense to me because it seems to directly follow from the island ages and when islands are available for colonization. So I wanted to use the island progression rule as kind of like a sanity check for this model that I was making, because I assumed that if I had made my model correctly, then I would observe the island progression pattern if I kind of, coded it the right way. But what I observed was a bunch of different phylogenetic patterns that were very inconsistent with each other. Even if I just ran the simulation pretty much the same way a bunch of different times, I got all kinds of different patterns. And so I was really puzzled by that. So I kind of forgot about it for a while, but then I thought to myself, wait, maybe this idea of how replicable should this pattern be is an interesting question. Maybe the fact that I'm finding really different results for the simulation is an interesting sort of result in and of itself. So I went back and tried to sort of recode my simulation so I could run it a little bit longer. And basically, all I'm doing is it's a macroevolutionary simulation. So I'm just simulating evolution at the species level and above. So my species are just little points that don't have a population size. They have a geographic range, but the geographic range is like a point in space. And then there's time steps where every species is kind of copied, and it's copied kind of with mutation. And the mutation is kind of random. And at every time step, each species is duplicated and mutated into new incipient species. And that incipient species will stick around if... Oh, I spelled species wrong here. The species will stick around if it's really far from all the other species in the XY dimensions, then it'll stay a new species. Or if some of its other traits are really different from all of the other species, and then it'll stay a new species. Huzzah. But if it's really close to all the other species and it's pretty similar to the species that it's close to, then it will not persist. So it'll go extinct. Wah wah. And each species has 27 characteristics. I guess they're not really characters. And it has kind of phylogenetic placeholders. The details of the model are not super duper important. I ended up it ended up that this system for keeping track of the phylogenetic branching order in the species ended up it didn't really work because R, which is the experimental language, it's the coding language that I was trying to run the simulation in, doesn't allow me to store numbers precisely that are more than 15 digits long. And so after 15 time steps, the simulation wouldn't calculate phylogenetic relatedness correctly. So I ended up doing my simulation in a different way that forced me to learn a whole new programming language called Julia. And good old Julia. Look at this. Good times. And some kind of scripting languages that are just in the Unix shell of Mac. And just a lot of stuff. But the cool thing was I could set up this simulation, I could script it so that it ran, thousands of times. And every time it ran, it would select new parameters from a random distribution that I selected. So the number of time steps that Kauai is emergent could be changed. Oahu, Maui, Hawaii. Starting richness was always 1. Evo length was always 28. But I could toggle the range radius, which is how far away an incipient species has to be to successfully allopatrically speciate. And I could I could mess with the thresholds for how sort of ecologically similar the species had to be if they were going to speciate ecologically, so if they were close to other species, but if they were different from them based on the niches that they were occupying. I could change the extinction rate, how many sort of niche axes are being partitioned. So if there's only 2 niche axes like pH and temperature, then it's harder for a lot of things to coexist in the same place than if there's like 5 different niche axes like pH, temperature, rainfall, how clayey the soil is, like a bunch of different ways of characterizing niches. How good the organisms are at dispersing could be really important. And then the island size could be really important. So I could run the simulation a bunch of times. So I could basically rewind the tape of life thousands of times just in a few hours because I could run the simulation a lot. And then I had to figure out a way to sort of quickly evaluate how much or how little the island progression rule was being violated. So I set up a series of kind of like true-false statements of testing whether the maximum phylogenetic distance between all these taxa was bigger than the maximum phylogenetic distance of just the taxa that were present on Hawaii, for example. And, is the maximum phylogenetic distance of all the taxa that are in Maui and Hawaii smaller than the maximum phylogenetic distance of all the taxa that are in Kauai and Oahu? So I wanted to set up a series of kind of true-false statements that were consistent with the island progression rule. And then I would sum all these sort of true-false statements that were true. So all the statements that I thought were kind of consistent with the island progression rule, I would be like, is this true? Is this true? Is this true? Is this true? And then I would add those up, and that would be kind of like the score that the prog sum. So the way to read these is like Kauai Oahu maximum phylogenetic distance is bigger than Oahu Maui Hawaii maximum phylogenetic distance. So this is bigger than Oahu Maui Hawaii distance. So there's a bunch of true-false statements. And then I would also look at the maximum and the median and then analyze the data for thousands and thousands of runs. So one of the things that really quickly comes out is that as you vary a lot of parameters at the same time, you get a really wide range of different outcomes. So the species richness of the Kauai, of the taxa that are found on Kauai at the end of the simulation runs varied, for example, from more than 4,000 taxa to really very, very few. So in the tens or down to zero in some cases if there was just total extinction. And often that was a function of range radius. So how many species could exist in the oldest island where the radiation started was mostly just a function of how far away the taxa had to be before they could allopatrically speciate. And the one thing that made the island progression rule more likely to be sort of adhered to was how far the islands were away from each other. So if all the islands were super duper like mashed close together in space, then the island progression rule would be less likely to be perfectly adhered to than if all the islands were really far apart from each other. So that kind of makes sense, right? Because one thing that could cause an island progression rule violation is if Maui was like super close to Kauai, and there could be back colonization that led directly back to the oldest island, for example. So that was a pattern that kind of made sense. You can also take a variety of statistical, tricks to just sort of generally explore the variables that are most predictive of different output variables. So what are the variables that are most predictive of the species richness on Kauai? What are the variables that are most predictive of the species richness in Hawaii? These are all classification and regression trees, which is kind of a fancy multivariate stats technique that's kind of based on it's sort of based on linear regression, really, ultimately. But these are just different ways of kind of quantifying the extent to which different parameters that I could vary would lead to different outcomes. And so, yeah, there were some surprises. Some things didn't have any effect at all that I thought was going to have an effect. So I thought that there would be an importance to limits of evolvability for somewhat complicated reasons that I'm not going to get into because I just want to make this kind of easy breezy. One cool thing that I did observe is if you plot the species richness in each island over time, over the course of a run, you can see this cool kind of exponential growth and then curving towards an S-curve of an equilibrium. And so this is actually really similar to the way population growth happens as it approaches a carrying capacity in an ecosystem, for example. You start in population growth, you see these kind of S-shaped curves, and it's kind of interesting. It's something that people have talked about as a potential feature of lineage through time plots, for example. So it's kind of cool. These data are consistent with the idea that there might be limits to species richness that are based on island area, even when speciation is the primary driver of species richness. So for those of you who have some familiarity with the equilibrium theory of island biogeography by MacArthur and Wilson, you know that colonization and extinction can interact to form an equilibrium species richness on islands, but speciation isn't really a part of the equilibrium theory of island biogeography as it's stated typically. So this kind of equilibrium of kind of a speciation area relationship is kind of interesting, or at least a diversification area relationship, because I'm not including, because there's extinction happening on these islands as well. That's kind of cool. And so this is just in one run for an archipelago. And then if you run a bunch of simulations over and over again with the exact same parameters, with the exact same island size, you see consistently pretty similar outcomes for the ending species richness for the oldest three islands. But then with Hawaii, the youngest island, you see more variability because that's the one that's most likely to not be colonized for very long. So the time to colonization can have a big impact on how species rich it becomes. So the presumably these instances were just cases where Hawaii was colonized relatively late just by chance, and so they didn't have a time to reach their equilibrium. So I don't want to, belabor the point too much, but I just wanted to give you all kind of a quick overview of the way I thought about trying to place the island progression rule within the context of, sort of a hypothesis testing simulation study. Ideally, what I was hoping was that I'd be able to apply some of these results to my understanding of the way speciation and diversity patterns play out in Palau, which is where I really want to focus doing my work. Palau is actually not a hotspot archipelago like Hawaii, so the pattern of island age is really different. There's a lot more islands than there are in Hawaii, and I study a variety of different organisms in Palau that may or may not be playing by the same rules. So land snails, ants, and I've also done some work on a couple of random other invertebrates like this arachnid group called schizomids. So I was hoping that these simulation studies would be really informative and that would kind of point a way forward for me to understand these diversity patterns in my study system a little bit better. But unfortunately, it just seems like it can be a little bit chaotic, and diversity patterns and biogeography can be a little bit harder to predict than I thought they would be. So I just wanted to talk about that a little bit. Thanks for listening. I'm going to turn this off and